When working with physical systems, we often have to perform integrals over volumes. A simple example of a volume integral would be one that evaluates the magnitude of some volume. Then we could imagine that we built the volume up out of very small bricks, or more mathematically, rectangular-sided boxes. So here I've got some toy bricks, and imagine that we're trying to sort of build up a pyramid shape here by progressively adding these little bricks onto the top of the surface that we're working on. And if I were to count all of these bricks, which are all the same size, and if I knew the size of the bricks, and they were approximating the shape that I was trying to integrate over here, the total number of these bricks and their volume would tell me the total volume that I'm looking at. So if we know how big the bricks are and how many it takes to fill the volume, then multiplying the number of bricks by their volume tells us the total volume. Obviously, if we could work with smaller bricks, we would get a better idea of the volume because we would be approximating the surface better.
So in volume integration, having divided our volume up into a collection of bricks, each perhaps of volume delta V, then if we add up all of these small volumes of all the bricks that fit within our larger volume, and if we index or label each of these bricks with some number, J here is the index, adding up all of these small volumes, these bricks that just fit into our large volume, would give us the total volume. And in the limit of very small bricks, this collection of all of these little bricks and their volumes added up would be the integral that gives us the total volume. So formally, the volume would be the integral over the volume of all of these little infinitesimal volumes, or infinitesimal bricks, and that would be formally the limit as the volume of those little bricks went to 0 of this sum of the volume of all of these bricks. Volume integral notation can be a little confusing, and there are various notations here that we use for the volume of the infinitesimal little bricks. And all of these have their shortcomings and can be confusing. If we use this one, well, we're not being very specific about what the integration variables are. We're just formally dividing the volume up into bricks and adding them up, but it doesn't tell us x and y and z and variables like that. This notation here is quite common, but a physicist would profoundly object to it because this does not have the right dimensions. If this r here is referring to position, then this dr trying to refer to the volume element does not appear to have the dimensions of meters cubed or volume. Nonetheless, this notation is sometimes used. And the notation here at least gets the dimensions right if we understand d cubed r to be somehow r cubed in terms of dimensions. That's also not terribly clear here. But like dr, both of these have the fault that they both seem to imply that this is a vector quantity here because we've used the vector r position in them. And in fact, that's not true. Both of these are scalar quantities. So all of these notations are used, but they all are rather unsatisfactory if we look at them from a fundamental point of view. Nonetheless, in practice, there's usually not too much confusion. Now, in doing a volume integral, we don't just want to evaluate the volume. We often want to evaluate something else, some quantity that we integrate over the volume. So we can integrate some quantity that is a function of position r. And a good example of that is density. So the number of kilograms per cubic meter. This might be the density of a cloud or something like that, that can vary with position. And we've used rho here, which is a common symbol used for density. So the Greek rho of r would be the density of the material within some volume. And if we integrate this up, if we add up the density times all the little volumes, we will get the total mass in the volume. And this would be, for physicists, this would be in kilograms, and this density would be in kilograms per cubic meter. So then, our total mass here is the integral over the volume of the density, and I've used the d cubed r notation here, but this is a volume element, so this is dimensionally correct, and this is an integral that gives us the mass, the total mass. Now, ideally, when we're doing volume integrals, we would like to reduce them somehow to the one-dimensional integrals that we tend to know how to perform. And this is sometimes possible. So, as I said, to evaluate these volume integrals, we would like to reduce them to one-dimensional integrals, a set of them, possibly nested, so we can do one after the other. And this can be done, at least for simple volumes, although in general it's not necessarily easy to do this. So a simple volume might be a cuboid here, or a cube, or something with rectangular faces. And with the rectangular faces, we can in fact divide up the integration this way. So this cuboid here might have a length xl in the x direction, and yl in the y direction, and zl in the z direction. And then to evaluate the total volume, we could in fact write this as three nested integrals over z, y, and x. So the innermost integral is this one over z, and it goes from whatever is the starting position in z here up to the final position, which is a distance zl further away. And then we've also got integrals dy and integrals dx here. So we can perform that z integral, and the answer for that z integral, integrating dz, just gives us zl when we integrate from zc to zc plus zl. And then we can go on and do the y integral, and integrating over y will give us yl. And then finally we can do the x integral, and integrating over x will give us xl. And the product of these three is, of course, the volume of this cuboid here. But I should stress that this is not always possible for other volumes. It's not always possible to separate integrals so simply into nested forms like this. We can also perform integrals over surfaces, and we can do that by dividing some surface up into patches. So here's one little patch of area delta A here on our surface, and we're interested in the total surface of the box. So we might be interested in what's the total area of the paint on the surface of the box, or just what's the area. So we can do that, and again, what we would do to get the actual integral would be to take the limit of very small patches. And here would be a surface integral. We've put S here to represent that we're integrating over the surface, and we've used dA as our surface element. And then the idea is that the integral would be the limit as delta A tends to 0 of the sum of the areas of all of these little patches on the surface. And again, there are many different notations that we can sometimes use for surface integrals with similar confusions to those that we had for volume integrals. And again, here R would be the position on the surface. So it's a vector position, but the real element here is a surface area element and does not have any vector character.